Hello, welcome to 13 Universal. This is A-level CIE Biology with Shedro, and we continue with Advanced Practical Skills Paper 3, Series 2. We'll continue to look at follow-up questions. So let's look at Paper 3 follow-up questions. We're going to be bringing you more questions, more solutions on Paper 3. So, but let's see this question. The grapes are fruit that contain high concentrations of soluble sugars such as sucrose, fructose, and glucose. Guys, don't forget that we'll not be able to do the real practical here. This is online, okay? Online class. But with time we'll show you how it is done. We won't be able to do it, okay? But just follow us and see the follow-up questions, how it is being solved, and the logic behind practicals. All right. So it says, let's start from the beginning again. It says grapes are fruit that contain high concentrations of soluble sugars such as sucrose, fructose, and glucose. The proportions of these sugars change as the grape mature. All right, it's gonna increase, it gets sweeter. Do you like grapes? I love grapes. Okay, said you will determine the concentrations of reducing sugars in a sample of grape extract by using concentrations of non-reducing sugars. So we use concentration of non-reducing sugars to estimate the concentration of unknown, right, grape extract, the sugar inside of it. So we're using standard curve. So I'm going to be using known concentrations to plot a curve, and then we use it to estimate the sugar concentration from grape extract. You are provided with the materials shown in table 1.1. So once you get into the lab, check this and check your bench. Is there anything labeled G there? That's grape extract, 20 ml. You have to check W, which is distilled water. So check before you start. This is R, which is 8% reducing sugar. All right. So none of this except for Benedict solution. None of this is hazardous except for this. So once you check it, you rinse your test tube, label them, and then the next thing you read the instruction. Okay. So here we're expected to um, produce different, all right, concentrations. Remember that we want to estimate the concentration of sugar in a fruit extract, grapefruit extract. So, but we need to plot a standard curve using known concentration. So we're diluting this. This is R, okay? This is the stock concentration, which is 8%. Is that okay? So we're doing serial dilution, and it is half fold, okay? So we're going to produce other concentrations using 8%, and it's going to be serial. Serial dilution is a stepwise dilution. So we're using this to produce this, use this to produce another one, and another one. Okay, stepwise dilution. There are things you need to know about cell dilution. Okay, once you find your V1, remember that in every dilution, there must be the volume that you are taking to dilute. Okay, we always have our C1, which is initial concentration, and we have our V1. This is dilution formula, guys. Initial volume equals C2. Is that okay? C2 V2. This is dilution formula, right? So if I do C1 over C2, that gives me dilution factor, right? Yeah, okay, and that's equal to V2 over V1. That's dilution factor. If you want to find a dilution factor, like here, we are to dilute by half, okay, half fold. So I already have 8%, which is this. So the next should be 8 divided by 2, which is 4%. Okay, 4%. Come with me, guys. So this should be 4%. All right, 4% of R. 4% of R here, right? So if I make another beaker, there's another beaker somewhere here, another beaker here, and I have another one. Let's add extra 4. Okay, so guys, come, let's do it. So oh yeah, maybe one more here or not. Okay, so this is going to be 2%, right? This is going to be, because 4 divided by 2, we're diluting by half, right? So that's 2%. That would be 1%, right? Percent. Put the percent there. Okay, 1% is 2%. So 1 divided by 2 gives us 0.5 because we're diluting by half. That's dilution factor. 0.5% divided by 2, that will give you 0.25. 0.25. All right. The last one should be 0.25. So that is 0.25 because we're diluting by half. That is dilution factor. So this is 0.25. Sorry for the background noise. Percent. So yes. So if I want to check my dilution factor, remember that this first one is 8, right? This is my C1. If I'm moving from that to that, this is my C2. So if I say 8 divided by 4, that's 2. Right? Remember that the final volume here, okay, is V2. And we've been given that, which is 20. How do I know that it is 20? From very beginning, you know that it's 20 cm cube. How am I supposed to know, guys? Okay, because of this principle that says that my V2 will always be, right, equal to V1, okay, plus volume of water. So V1 is the volume of the stock I'm diluting, but I have to add water to it. Dilution involves addition of water. So I add water to something, I've diluted it. Okay, so from beginning here, they have given us what the V2 is. Okay, so V2 here, look at it. That is 20 plus 0. 20 plus 0 is 20, which is V2. So my V2 is already known, guys. All right, so let's roll it. So what I need to get is this V1. I need to write this V1 here, this V1. That's what I need to get. And once you get the first V1, it's the same. So because you're going to use this to produce this, use this to produce this, use this to produce this, this, then this. But remember that each time you're going to add water to dilute. Okay. So if I have this, look, I'm going to take from here. So add water to this, right? Take from here. Okay, I want to know the volume because the same volume is the same thing. Once you find V1, you have found volume of water. Okay, you have found it. Did you get it? So take from here, add here. Okay, just that way. So the same volume, so it continues, guys. It continues that way. All right, serial. So stepwise, you use the preceding solution to prepare the concentration of the succeeding solution, right? So okay, so let's get V1. So don't forget that from this formula, right, our V1 is what we need. We already know everything. V1 is just calculate it. You need only one V1, okay, and you're fine, sorted. C2, okay, V2, C2, V2, all over C1. All right, so if I'm moving from, this is my C1 8%, C2 4%, V2 is 20. So just put it here, that's all. Therefore it's going to be C2 is 4 times what? 4 times V2, which is 20, right, divided by C1, which is 8. So what do we have, guys? 4 times 20 is 80, right? Good. 80 divided by 8 gives me 10. So my V1 basically becomes 10. So 10 cm cube, that's the volume of each concentration I'm going to be removing to make the next one. And since my V2 is 20, so once I take 10 of a solution, I'll add 10 of water. Is that okay? To make it 20. So I know this is 20. If I have 10 of these, to make it, this must be 10 also. All right. So guys, so that means that what should be here is 10. But you see, this is going to 10 cm cube. That's what I'm taking here. 10 cm cube. This is what you're going to do in the lab before you start the experiment. Okay? 10 cm cube of this 8. Okay? Because I want to use it to make 4. So 10 cm cube of 8%. And if I take 10 cm cube to make it 20, I have to add 10 cm cube of water to get, so that everything becomes 20. Water is W of water, okay? Of W, distilled water. So once you get the first one, others are simple. It's the first one that matters. The rest is repetition, okay? So I take 10 cm cube of 8, add 10 cm cube of water to make 4%. So I'll take 10 cm cube of 4%. So what I'm going to write is 10 cm cube of 4%, just like I wrote here. 10 cm cube of 8. So 10 cm cube of 4%, I'll add 10 cm cube of water to form 2. So I'll take 10 cm cube of 2%, add 10 cm cube of water to make 1%. 10 cm cube of 1%, 10 cm cube of water to make 0.5, 10 cm cube of what? Of 0.5%, and 10 cm cube of 0.25, no, of water to make 0.25. So what I'm going to have here left here is 20 cm cube of 0.25. For the rest here, all right, what I have left here is 10 cm cube. You write 10 cm cube of 4% left. It was 20, but when I took out 10 cm cube of 4% left. So this was 20. When I took out 10, okay, what is left is 10 cm cube of 2%. This is the same thing, 10 cm cube of 1%, 10 cm cube of 0.5%. This is the only one that is 20 cm cube of 0.25% because I didn't take out any. So once you find from here to here is the same, that's for serial dilution. These are my V1. V1 is the same, okay, and volume of water is the same. Just keep repeating it, okay. All right, guys, let's move to the next question. So that's all. So we know our concentration: 4%, 2%, 1%, 0.5, 0.25%. All right. So look at it. See what the mass scheme says. Correct concentration: 4%, 2%, 1%. So just 4 is enough. All right. 1, 2, 3, 4. So shows transfer of 10 cm. You have to show transfer of 10 cm cube. All right. Bigger from previous, from here to here. Right, and then from here to here, and then also have to show 10 cm of water that is being added to each beaker. Just 3 marks, guys. That's a lot. All right, let's go to the next question. Now these are instructions. Sorry for background noise. It's a carry out 1 to step 16. Let's go. Set up a water bath and heat to boiling, ready for step 6 and step 14. So you set it up, prepare the concentration of reducing sugar solution as shown. We have seen that. Label test tubes. So please follow the instructions with concentration shown in figure 1.2. So these are things we're going to do. Then step 4 says put 2 cm cube of Benedict solution B into the same test tube, shake gently to mix. That means the same test tube you put your solution, that's where you put Benedict solution. Put this test tube, all right, put this test tube. So guys, so the same test tube, all right, you added your solution, add Benedict solution there, 2 cm cube, all right. So you go on, measure the time taken to the first appearance of a color change. You remember that in test solution, in testing Benedict solution, you add 2 ml of test solution into a test tube. Remember that is what we are doing here, okay. So you put 2 ml here of test solution, and then now add 2 ml of Benedict solution to this, right, and then you now heat. So they say you should measure the time for first appearance of color in the test tube, and then if there is no color change after 120 seconds, stop timing and record as more than 120. All right, and then step 8, record the result from step 7 in step 1 AII. Okay. So guys, so remove the test tube from the water, put the test tube in the test tube rack. Repeat step 4 to 9 with remaining concentration of reducing sugar, and then of course record the answer, guys. Now the first thing you have to note here, anytime you're reading instruction, the first thing you have to note here is number one, because in every experiment we have the independent variable, which is the one you're changing, and dependent variable. So the question is, what is your independent variable here? Your independent variable here is concentration, because that's the one you're varying. So we have 8, 4, 2, 1, 0.5. The dependent variable is one you are measuring. What are we measuring here? What they say you should measure, guys? What they say you should measure? Check. Yeah, you got it. They say you should measure, see, measure the time taken to the first appearance of a color. So once you know that, and they say record your result. So whatever you got in your result, guys, I want us to have it clearly sorted out. Okay? Pardon me, I'm going to draw this here. Our table, you must draw enclosed table for all biology experiment, all science experiment. Okay, pardon the diagram, but this is the table must be enclosed. Then you have heading. Okay, so we have the first column there. This must be concentration. That's the independent variable. So you have to label it here. You have to write it. That's concentration of sucrose. The concentration of M, I guess. Okay, that's M. Concentration of M, and that is in percentage. Okay, in percentage. So you have to put unit there, and this is time for color change. Time for first appearance of color. Time, all right, for first appearance of color, and that time is in seconds. Seconds. You must put unit. Okay. Now, it's also good if you do the first trial, second trial, and find the mean. Okay. Look at it. So, yeah, this is our first trial. This is second trial. Okay. Table, and this is third trial. If you have the time, of course, that's the ideal thing to do. And then this is the mean. Calculate it. Very important. So this is the mean. So then you have the different concentrations. So don't forget that this is our 8. Okay, this is how your table should appear. This is 8. Sorry. Let me clean it off. Yes. So you have to know how to record your result. This is 8. Okay. The next. Okay. Let's draw the row first. Look at this. How many rows? About 4 more rows. Okay. Yes. 4 more rows. So you can see that. So we have 8. We have 4. We have 2%. We have 1%. We have 0.5. And of course, the last one maybe 0. That's our 0 is our control experiment. Okay, it's a control experiment. So this is how your results should appear. And guys, please don't forget that as concentration decreases, time for color change should increase. As concentration decreases, time for color change should increase. That's the trend. If it doesn't follow it, all right, it will reduce the mark you get here. All right, but if you follow the instructions very well, you will get the appropriate trend. All right, because if you have more concentration of reducing sugar, all right, of course concentration affects rate of reaction. More concentration, more collision, and then the faster the reaction. So that means as I move from 8 to 4, the time, it will take a longer time, all right, for color change in 4 than 8. The same thing. All right, so look at what the math scheme says here. Your heading for independent variable percentage concentration of reducing sugar, all right, and no unit in body of table. You don't write, yes, I forgot to say it, you don't write unit in the body of table, you write unit on the heading. Okay, and that is it. Now heading of dependent variable seconds, no unit in the body of table. Results for all concentration, look at it. Time for the highest concentration of reducing sugar should be less than time for the lowest, all right? Yeah, so you have to check that. Result recorded in whole number. 5 marks for that. That's a lot, guys. So we continue the experiment. It says identify one source of error in step 7. Step 7 is when you measure, all right, you observe color change, all right? It is difficult to know or to judge when color changes. That's it. Intermittent color change is always difficult to judge the first color change because it's subjective. You're using your eyes. So how do you improve on this? How you improve on this? Use colorimeter, right? Or you can use a white um, paper behind the test tube. All right. All right, let's go to the next. We'll continue. To determine the concentration of reducing sugar in grape extract G, you will need to test a sample of the extract. State the volume of grape extract that we use to test for reducing sugar. Now, remember that in the other concentrations, we use 2 cm cube. So you're also going to use 2 cm cube here, all right? So that has to be standardized. Do you get? So if you change it, it's going to affect the result. So this is a key variable. Volume of the solution should be the same in all scientific experiment to have key variables. Right, so 2 cm cube. Now we'll continue step 11. Label a test tube G. Transfer the volume of grape extract G that is stated in AIV into test tube G. So you put it in test tube. What did you put? 2 cm cube of grape solution be into the same test tube. Shake gently to mix. Step 14. Put this test tube in the boiling water, but start timing. All right, and then measure the time taken for the first appearance of a color change, just like you did to others. If there's no color change, the same thing. Yes, guys. So record the result. You record the result. Whatever your G is, record it. Okay. So record the time taken for the first color change in test tube G. You also record it. So for this experiment, it depends on. So it's a record a time G between recorded time for 4%. So it's trying to say that 4% and 1%, right? G is in between it. Okay. This very, yeah, guys. So you can see that. So go on. So the concentration of reducing sugar will continue in G can be estimated using a graph. Like I told you, use a standard curve to record it. Draw a graph of the results shown, the results you recorded on the grid using a line of best fit. Okay. The axes have been labeled for you. Look at this, a sharp pencil. So it uses a scale. Okay. For percentage, 2 cm cube for 2 cm, no, 2 unit for 2 cm here. Or I can choose based on your result. Choose here. Very important. All right. So see, your graph should on x-axis 2 cm to label it. So this is based on, and they use thin lines. And don't forget that we connect every dot in the graph. Connect it. All right. Use your graph to estimate the percentage concentration of reducing sugar G. So yes, guys, you know how to do this. If this is your graph, all right, just to show you, this is concentration. We don't know it. Okay, and this is time for color change. This is time. Don't forget, you must put unit there. This is seconds. This is percentage. Okay, this percentage. So let's assume that they have negative correlation, something like this. Okay, so if whatever you get here is your G, this is your G, you don't know the concentration. You're using this curve to know it. So go to the graph, trace it. Wherever it touches the graph, take it down. That is going to be your concentration of G. Okay, because we're using this curve to estimate the concentration of G. You're using it. All right, guys. So show on your graph how you determine the answer sheet. You then record the percentage there. Show interpolation of, yeah, you must show the interpolation. Yeah. Okay, how you interpolated it. Yeah. So correct estimate from the graph, just 2 marks. That's a lot, guys. So that's how you would modify this investigation to obtain a more accurate estimate for concentration of reducing sugars. So what you just do, just like any suggestion, you have to, guys, have to create more concentrations around where you find G. If G is between 4 and 2, you can use 10-fold serial dilution, all right, to create it. And repeat and find the mean. Use cardboard, all right. Okay, look at this question. If you're going to plot a graph here, this is your independent variable. So concentration of resin sugar in grape changes as the graph gets older. So this affects this. So as it gets older, the sugar will, okay. Usually this is the first column is the independent variable. All right. So you plot it here. This is your dependent concentration. This is your independent, which is age of the grape. All right, just to tell you, we're going to spend more time on this later. X-axis age of graph and days, y-axis percentage of concentration of sugar. So you plot it and they connect the dots. So you can now use estimated, the one estimated from G, you and your graph to estimate the age of the graph. So compare the concentration of your G and then use it to find the age of G. All right, write it down there. So you use your graph, like I showed you before. Okay, so it's a grapes contain starch as well as reducing sugars. In a study, the concentration of amylase in grape was measured as grape age. The result is shown below. You can see that as grape age, what happens to concentration of amylase? It increases. So what happens? Use the data in figure 1 point and to suggest the possible explanation for the change in concentration resin sugar in grapes. Okay, so as your grape increases, as your grape ages, what happens is that the concentration of sugar increases. Why? Because amylase will break down more starch. All right, amylase breaks down more starch to form it. All right, increase as grape age. You can see amylase hydrolyzes starch into resin sugar. You can see that. More amylase leads to an increase in resin sugar. You can see that. So 3 marks. So guys, sorry for noisy background, but want to hear a comment. We're going to do more excellent videos. Okay, stay with us. This is Shedro. Bye.